Can I start? I mean,
Can start. Thank you.
yes.
Yes.
Yes. Good morning, ladies and gentlemen. Good morning, dear colleagues and friends. I am happy to be able to participate in COSA conference, even if only remotely. I hope that in the near future, there will be an opportunity for face-to-face communication. I wish successful work for the conference and good luck to all participants. I also thank the organizers of the conference for their kind invitation. And if the communication is all right, I can start. Presentation, please. Okay. Okay. Boolean-valued analysis and positivity. Boolean-valued analysis was preceded. Boolean-valued analysis was preceded by three remarkable events. That is, Cantor continuum hypothesis, Gödel's consistency proof of continuum hypothesis, and Cohen consistency proof of the negation of continuum hypothesis. This result culminated in the invention of Boolean-valued analysis, Boolean-valued models of set theory. And then another story began. A burst into independence proofs and the vehement development of Boolean-valued analysis. My plan is the following. I will take a very quick look at Boolean-valued machinery and then outline briefly three applications of Boolean-valued models to positivity, namely maharan operators, to injective Banach lattices, and to Weckstedt problem. Thus, the story I'm going to tell started in 1878 when Cantor formulated his famous continuum hypothesis. That is, any subset of unit interval or any subset of real line is either finite or countable or continuum. Continuum means that the set is the bijective image of the real line of the unit interval. In 1939, Gödel proved that if mathematics is correct, then it is correct with the continuum hypothesis. More precisely, if Zermelo-Fraenkel set theory is consistent, then Zermelo-Fraenkel theory with axiom of choice and with continuum hypothesis is also consistent. And 1963, Cohen proved that if the Zermelo-Fraenkel set theory is consistent, and it is consistent with the negation of continuum hypothesis. Intention to simplify the Cohen's method, forcing method, and Cohen's brilliant achievement for working mathematicians led to discovery of Boolean-valued models. This was done by Dana Scott, Robert Soloway, and independently by Peter Wopinka. Dana Scott wrote in 1977 to express his admiration by the Boolean-valued models. It was in 1963 that we were hit by a real bomb. However, when Paul Cohen discovered his method of forcing, which started a long chain reaction of independent results, set theory could never be the same after Cohen. But earlier, Dana Scott foresaw the role of Boolean-valued models in mathematics. We must ask whether there is any interest in these non-standard models aside from the independence proof. That is, do they have any mathematical interest? The answer must be yes, but we cannot yet give a really good arguments. And these really arguments appeared 8 years later. In 1977, Eugene Gordon, a young teacher of Lobachevsky Nizhny Novgorod State University, published the short note in which he proved that the objects representing reals in a Boolean-valued model of set theory can be endowed with the structure of vector space and order relation so that it becomes a universally complete vector lattice. This was done in this short paper, and more precisely, this result can be stated as follows. The interpretation of the reals in an appropriate Boolean-valued model of set theory is a universally complete vector lattice with the given Boolean algebra of bands. In the same year, at the Symposium on Application of Sheaf Theory to Logic, Algebra, and Analysis, Gaise Takeuchi, a renowned expert in proof theory, observed that the vector lattice of measurable functions can be considered as the Boolean-valued reals, and the commutative algebra of unbounded self-adjoint operators in Hilbert space is another sample of Boolean-valued reals. These results were presented in his famous book, published in 1978, Two Applications of Logic to Mathematics. These two events marked the birth of a new section of analysis, which Takeuchi designated by the term Boolean-valued analysis. So, Boolean-valued analysis is a branch of functional analysis which uses a special model theoretic technique and consists in studying the properties of a mathematical object by means of comparison between its representation to different set theoretic models whose construction utilizes distinct Boolean algebras. These two models are usually taken as von Neumann universe. This is the world of conventional sets, and the Boolean-valued universe specially constructed, specially selected, constructed over an arbitrarily complete Boolean algebra B. V, so von Neumann universe, it consists of naive set, that is the conventional set. The von Neumann universe is the world in which we do our mathematics, our everyday mathematics. And these objects in von Neumann universe we will call standard objects, whilst the objects in Boolean-valued universe we will call non-standard objects. And the comparison between these two universes can be performed by means of two operations: ascent, which acts from the von Neumann universe to Boolean-valued universe. This operation sends any standard object to non-standard object, which will be called standard name or standard image of the standard object X. And descent, which acts in the opposite direction, which sends any non-standard Boolean valued object X italic into standard object X italic down arrow. Okay, the ascending descending machinery enables one to carry out interplay between these two universes. And now we have to know how to verify different mathematical statements within Boolean valued models. First question, how to make statements about the elements of Boolean valued model. We take any Zermelo-Fraenkel formula, Zermelo-Fraenkel set theory, formula of Zermelo-Fraenkel set theory, phi with variables y, u1 and un, and replace the variables by elements of the Boolean valued model, VB. Then we have some statement about the elements of Boolean valued universe. How to verify whether or not this statement about the elements of VB is true. There is a natural way of assigning to each statement of one element of B, the Boolean truth value, so-called Boolean truth value. This is an element of the Boolean algebra B. And now we say that the statement phi about the element of Boolean valued model x1, xn is provable or is true within Boolean valued model if this Boolean truth value is the top element of Boolean algebra B. Okay. And now the main principle in Boolean valued analysis, the transfer principle, state that all the theorem of Zermelo-Fraenkel theory, set theory with choice are true in Boolean valued model. This means that any theorem of Zermelo-Fraenkel set theory written as a set theoretic formula has the Boolean truth value equal to unity of the Boolean algebra. And the large part of the Boolean valued proof, Boolean valued approach is in calculating of Boolean truth values. Okay, now how does the Boolean value transfer principle work? Assume that we have two classes of objects. One class of object, X bold-faced, consists of standard object. It is a subclass of the Boolean of von Neumann universe. And the second class is double struct X, consists with Boolean valued objects, so, that is non-standard objects. Now, suppose that we are able to prove the following representation, Boolean valued representation result. Every X, standard X, embeds into the Boolean valued model, becoming an object X italic in Boolean valued model. Then the Boolean value transfer principle say that every theorem about X italic within Zermelo-Fraenkel set theory has its counterpart for the original object X italic, object X interpreted as a Boolean valued object X italic. And then Boolean valued machinery enables us to translate theorems about X italic, Boolean valued theorems about X italic to corresponding result concerning the initial object X. This is performed by ascending descending procedure and the principle of Boolean valued analysis. And there are two books when the details and results and so on can be found. Now, I will try to explain the above method, above approach. On this picture, we have two universes, the von Neumann universe, the class of usual sets, and we have another universe, Boolean-valued universe. If we take any object in von Neumann universe, for example, the field of reals, then it can be embedded into the Boolean-valued model, and the result will be some object that is the standard name of the reals. At the same time, in the Boolean-valued model, we have the field of reals, internal field of reals in Boolean-valued models. We can descend this object and obtain some set in von Neumann, standard set in von Neumann universe. We can descend also the operation, addition and multiplication, and the order relation, so that we obtain some, not only a set, but some algebraic structure. And relationship between these four objects is the problem of Boolean-valued analysis. So, and translating from von Neumann universe to Boolean-valued universe and vice versa, we can go to some interesting results. Now, this is the precise statement of theorem which was proved by Eugene Gordon in 1977, that if R italic is the field of reals in Boolean-valued model VB, then its standard name is this dense subfield in the internal field of reals in Boolean-valued model VB. This is an internal statement, and now an external statement. The algebraic structure, descent of R italic with descended operation and order relation, is a universal complete vector lattice. And there is a third statement which says that the structure, internal, external, are there is a relationship between these structures by means of the Boolean isomorphism from B to the Boolean value of all band projection of the R down arrow like this. These equivalences, the left-hand side are standard statements, and the right-hand side are internal statement with the Boolean truth value. So these relations enable us to translate statements from one universe to another. And maybe this picture also will be useful for understanding. Imagine that two observers watch some object, one with naked eye and the second with a kind of Boolean value telescope. And the observer with a naked eye see that I see universally complete vector lattice. But the observer with the Boolean value telescope says that, you know, I see the field of reals, the reals. So talking among themselves, they comparing their conclusion, they can discover some interesting results. Okay. Now, there are many problems that were solved with help of Boolean-valued models. I indicate only 6 of them, and highlighted are the topics that I will be discussed later. So intrinsic characterization of subdifferential. It was stated in 1976 and in 1982 was solved by Kusraev. General disintegration in Kantorowicz spaces, it stems from Yoff-11 and was solved in 1984. Kusraev. Kaplansky problem posed in 1953 was solved by Ozawa in 1984. So order boundedness of band preserving operators, the Wickstead problem. Okay, I will speak in details about this. Maharan extension of a positive operator stems from Luxemburg and Shep, and was solved by 3 authors in 1988 by means of Boolean-valued models. Also, this problem was solved by Ben de Pachter by standard means. And the classification of injective Banach letters stems from Lotz and Cartwright, and solved by means of Boolean-valued models in 2012. Okay. Now, the first topic is Maharan operators. Okay, and details can be found in these references, in these books. Okay, the Maharan operator is an ordered continuous linear operator between vector lattices whose modulus has the Maharan property. Maharan property is just the property interval preserving. So Maharan operator is an interval order continuous operator whose modulus is interval preserving. Okay, this is not, I can omit this. So to study Maharan operators by means of Boolean-valued analysis, according to the general scheme, we have to prove some Boolean-valued representation theorem, and this can be worded as follows. Every Maharan operators can be embedded in appropriate Boolean-valued model, turning thereby into an ordered continuous functionals. Okay, if so, we have many interesting results about ordered continuous linear functionals. For example, Nakano carrier theorem, given two ordered continuous functionals f and g, the equivalence holds f is disjoint, f and g are disjoint if and only if their carriers are disjoint. Radon-Nikodym theorem for any pair of functionals fg on order complete vector lattice, if the modulus of g is less or equal than f, then g is the composition of f and some orthomorphism. And Hahn decomposition theorem tells us that any order continuous linear functional can, for any order continuous linear functionals, positive part and negative part of functional can be represented as composition of f with some band projection and the complemented projection. Now, the Nakano carrier theorem, Radon-Nikodym theorem, and Hahn decomposition theorem are valid for Maharan operators. These theorems were proved in joint work by Luxemburg and Shep, and another theorem, another paper by Luxembourg and De Pachte, in which maharan extension was maharan extension of positive operator was done. Okay, and a few remarks about historical remark about maharan and Luxembourg. The concept of maharan operator stems from the article by Dorothy Maharan on the representation of positive operators. These papers were published in 1953 and 55, and it was a very interesting and important contribution to positive operator. And Luxembourg was the first to appreciate Maharan's contribution in his joint, above mentioned joint article, Shep and De Pachte. Some portion of Maharan theory was extended to positive operator. Luxembourg was also a pioneer of and promoter of blending model theory and functional analysis. He pointed out that the maharan operators may play a fundamental role not only in the theory of positive operators, but also in Boolean-valued analysis. This was done in Maharan Universal Volume, published in 1989. Okay. And now the representation, Boolean-valued representation of maharan operators. Without any details, this theorem tells us that any maharan operators can be embedded, can be embedded into the Boolean-valued models, and then it became a continuous functional tau. So the descent of this order continuous functionals is just our initial maharan operator. So, and now by transfer principle, we can conclude that any theorem which can be proved about order continuous functionals within Zermelo-Fraenkel theory have its counterpart for maharan operators. And as an example, we can give new Boolean-valued proofs of the listed theorem proved by Luxembourg and Shep. And as a new application, I will mark the so-called Strassen disintegration theorem. A range of important questions in convex analysis and probability theory is connected with Strassen type disintegration theorems. Strassen type disintegration theorem means that if there is a linear functional x prime, and which is majorized by integral convex or sublinear functionals, that is, this is the integral of the measurable family of sublinear functional p omega, then there exists a measurable family of linear functionals x omega, so that x prime is representable as an integral of this family of linear functions x prime omega, so that each of them x prime omega is majorized by p omega. So an abstract form of this disintegration theorem for operators looks like follow like this. Sublinear operator is the operator which is sub-additive and positive homogeneous. So dp means the set of linear operators majorizing by sublinear operator. So, and the composition of operator T and the set is the set of composition T is when S is any member of DP. Okay, now the following formula that so this set of majorants is called also the subdifferential or support set. So the support set of the composition is the composition of support sets. Okay, this rule is also called the disintegration formula, and it is true if and only if when T is a maharan operators. So the special case when T is an integration operator, we obtain a different kind of structural disintegration formula. Okay, now about injective Banach lattices. All the results and notions and related theorems can be found in this reference. What is an injective Banach lattice? An injective Banach lattice is a real Banach lattice X such that for any y, y0 and t, y is a Banach lattice, y0 is a closed sublattice of y, and t0 is a positive linear operator from y0 to x. And for any such triple, there exists a positive linear operator, which is the norm preserving extension of T0. So this amounts to saying that this diagram is commutative. Okay. Injective Banach lattices were introduced by Lotz. In his paper, this one, he indicated two important classes of injective Banach lattices. First was that the kin-complete AM space with the unit is an injective Banach lattice. So equivalent to CK space is an injective Banach lattice where K is an extremely disconnected Hausdorff compact space. And the second example was that every AL space is also an injective Banach lattice. The first result is not surprising because CK is an injected object in the category of Banach spaces and isometries. And the second one shows that there is an essential difference between injective Banach lattices and injective Banach spaces, because C of K is an only injective space in the category of Banach spaces. Okay. I'll mention briefly main contributors. Cartwright found the geometric characterization of injective Banach lattices, the properties splitting property and the finite order intersection property will characterize injective Banach lattices. And Haydn discovered that injective Banach lattice has a mixed AM-AL structure and proved three representation theorem for injective Banach lattices. Another important contribution was made by several others: Arendt, Busquets, Lindenstrauss, Zavriri, Manchini, and Wickstedt. So now about the Boolean-valued approach. Boolean-valued approach was performed in this paper, and again, according to the general scheme, first we have to prove some representation theorem, and this theorem sounds as follows. Every injective Banach lattice embeds into an appropriate Boolean-valued model, becoming an AL space. And then the transfer principle states that every theorem about AL space within Zermelo-Frankel set theory has its counterpart for the original injective Banach lattice interpreted as a Boolean-valued AL space. So the machinery enables us to translate theorems from AL space to injective Banach lattices. This is the general scheme. Now, what sort of result we can obtain? For example, we have the following representation result. For a Banach lattice X, the following assertions are equivalent. X is injective Banach lattice, and the second statement is worded as follows. There is a Dedekind complete AM space lambda with a unit and strictly positive maharan operators phi from X to lambda with the Levy property such that the representation holds. The norm of X in X is then the supremum norm of phi of module X. This is the representation result, which generalize all the three representation results by Hayden. Okay, and one more application about classification of AL space. First, I recall the Kakutani-Maharan representation theorem. Any AL space at X can be represented as follow. So, without any data, I can say that any AL space it can be built from this from the Banach lattices of summable families and Lebesgue space L1. L1 0 1 gamma means the product of gamma copies of unit interval with Lebesgue measure. Okay, so L1 atomic and non-atomic are the building blocks for general, they are building block for any AL space, and now the Boolean-valued transfer principle enables us to state that CK space and L1 space, atomic and non-atomic, are building blocks for any general injective Banach lattice. The precise statement looks like this, and any injective Banach lattice can be represented as this direct sum of two components. First component is composed by L1 summable families, and lambda alpha is AL space. So, and the second non-atomic part is composed by the same the same kind, but with instead of atomic L1, we have non-atomic L1 spaces. Okay, discovery by Haydn that any injected Banach lattice have a mixed structure, ALAM structure, we can see in this representation. Now the last topic is the Wickstead problem. So I have about 15 minutes. Yeah. Good. Okay. I recall that the band preserving operator is an operator such that every band is an invariant subspace of this operator. X is a vector lattice, and so the vector lattice is named a Wickstead lattice if every band preserving linear operator is order bounded. And the problem is to describe the class W of Wickstead lattices. Wickstead lattices. In its full generality, the Wickstead problem is still unsettled, while it is very well understood for universally complete vector lattices. So I will speak only about universally complete vector lattice, and the Dedekind complete vector lattice is universally complete if it is also laterally complete, that is, any family of pairs disjoint positive element has this superelement. Now, two more definitions. A Boolean algebra B is said to be sigma distributive if for any double sequence BMN we have the following equation. Phi is the set of all functions from naturals to naturals. Okay, so the infinite lattice operations are permutable in such a way. This is sigma complete Boolean algebra. And the vector lattice is locally one-dimensional if for any pair of non-disjoint elements, x1, x2, there exist non-zero components, u1, u2, of these elements respectively, such that u1 and u2 are proportional. For universally complete vector lattices with order unit, this amount to saying that every positive element is representable as a step function. That is, we take a pairwise disjoint family of band projections, then we take the corresponding components of unity and multiply by real numbers, and the sum is the step function. So every x is a step function or step element. Okay. Now, in 1977, Wickstead raised the problem, this problem, when all band preserving operators are order bounded in vector lattice. In 1979, three authors found an example of unbounded band preserving operators. And the five authors obtained the following solution to Wickstead problem. That the vector lattice, universally complete vector lattice X is the Wickstead lattice if and only if it is locally one-dimensional. And then 1993, Wickstead posed the next problem. Is it true that locally one-dimensional vector lattice is the same an atomic vector lattice? In 1995, Gutmann settled the problem. He proved that X is locally one-dimensional if and only if its Boolean algebra of bands is sigma distributive. And X is a Wickstead lattice if and only if the same Boolean algebra of band projection is sigma distributive. Gutmann also showed that there is an atomless locally one-dimensional universally complete vector lattice. So this was the complete solution of Wickstead problem, but Boolean-valued approach to Wickstead problem reveals some new possibilities and new results. And as usual, if we speak about Boolean-valued approach, we have to prove some representation theorem. And this representation theorem about Wickstead problem, representation of band-preserving linear operators, reduces the Wickstead problem to study of surprisingly Cauchy functional equations. Cauchy functional equations are well-known equations. The solutions of Cauchy functional equations are additive functions that okay, and it is well known also that the continuous solutions of Cauchy functional equation are of such kind, Cx, so linear functions, okay, and this is the same to that the quotient f of x by x is a constant, So it is easy to see that if f is an additive function, that is, f is the solution of Cauchy functional equation, then it is also Q homogeneous. And this fact motivates the study of simultaneous functional equations, additivity, first equations, and homogeneity, the second equations. And the equation is considered on in the field F and its subfield P. So homogeneity is with respect to field P, and the additivity holds on the whole field F. Okay. Now the Boolean-valued representation, I mentioned it also, says that if we take the field of reals within Boolean-valued model are italic, and this denotes the additive functions in R italic, which are homogeneous with respect to standard name of the reals, or in other words, with respect to standard reals. And if and BPX is the set of band-preserving linear operators on X. Now, if X is the descent of R, descent of internal reals, then these two objects are isomorphic. In other words, any band-preserving linear operators in the universally complete vector lattice X is the descent of the function, which is the internal function, which is the solution to Cauchy functional equations in Boolean-valued model, and also it is homogeneous. Boolean-valued representation principle, and by transfer principle, the Wickstead problem is reduced to asking whether these internal functions, additive functions, standardly homogeneous if there is a discontinuous function which is the solution of the Cauchy functional equations, and also is standardly additive. Okay. So, and the theorem tells us that no discontinuous standard linear function in R italic, there is no discontinuous such function if and only if the internal field of reals coincide with the standard fields of reals. Okay. So I omit the proof, but I say that it is very easy to prove using Hamel basis. If these two fields do not coincide, then R italic can be considered as vector space over the subfield of standard reals, and this vector space has Hamel basis, which contains more than one element, and defining on two elements in such a way, we can continue this function from basis Hamel to linear function on the whole of R italic, and so this resulting function will be discontinuous because of violation of this property. Okay. And now this is another proof of Gutmann's result. So, but we can consider some other problems of similar kind. For example, if we want to do the same, we can state the Wickstead problem using derivations instead of linear operators, sorry. And then the problem have also interesting solution, and okay. So a derivation is the linear operators in F algebra, which satisfy the following Leibniz rule. Okay, and again we can prove the representation theorem that any derivation on a universally complete vector lattice can be represented as the descent of the internal derivation in Boolean-valued models, derivation in the Boolean-valued reals. Okay, so then we can prove the similar lemma that for complexes, that internal complexes is not equal to standard complexes. Then there exists derivation in the field of internal field of complexes, which is homogeneous with respect to standard complexes. And using the same machinery, we can obtain the following results. So we have that the complex vector lattice is a vector lattice. The following are equivalent. First, the vector universally complete vector lattice X is a Wickstead lattice. Second, X is a locally one-dimensional. Third, B, the Boolean algebra of bands is sigma distributive. X has no non-trivial R derivation. Complex vector lattice XC has no non-trivial C derivations. And the similar assertion about band-preserving automorphisms. So this was rather surprising because many people were interested in the existence of non-order bounded derivations on not only on F algebra but different algebra, for example, von Neumann algebras and so on. So for them, this result was rather surprising. So that's all. Thank you very much.
Oh, it's okay. I'm sorry because there are policemen asking for security of all these participants. So I have to handle with them also. So sorry. Now, thank you for your speak. And it was very clear for I think that I understand many things that I miss for much years. And just this diagram at the first time when you are coming, when you are starting from R, going to the Boolean universe, and in the dense subset R prime, I think, going there for the higher one and coming back to the universally complete real space. It was very clear. I thank you because now I understand how this machinery works and thank you for this. So I think that Bruce has a question. Yeah. Yes, I'll start. You have it. Okay. Spider. Say anything?
Okay, Professor Kusraev, thank you very much for the broad and interesting lecture. I have a comment and maybe a question. So the injective Banach lattices that you consider in your talk can be somehow considered as the injective objects in the category of Banach lattices when the morphisms are the positive maps, the positive linear maps. And relatively recently, we have been considering the same kind of object, but considering them within the category of Banach lattices, where the morphisms now are lattice homomorphisms. So not only positive maps, but lattice homomorphisms. And well, it was observed already by Ben de Pachter and Tony Wickstead that injective objects in this category cannot exist. But one can consider some restricted families. So one could consider, for instance, the class of separably injective Banach lattices. And well, as I said, recently we could prove that these objects exist. So one can construct separably injective Banach lattices where you can, you can extend lattice homomorphisms as long as you stay within separable, the domain of your, the domain of your extension is separable. So basically we have only two kinds of separably injective lattices. We know that some L1 spaces on some, if you take a sufficiently large power of the interval 0, 1, and you take L1 over there with the probability, with the product probability measure, this is separably injective in the sense I'm referring. And we have another sorts of examples, but these are completely wild and I think interesting to understand. So I was wondering whether vector valued analysis could be helpful somehow to say something about this class of spaces, if you have thought of it or.
Thank you. If I'm not mistaken, Wolfgang Rarent proved that the injective objects are the same independently, consider we positive operators as morphism or lattice homomorphism as morphism. Am I right?
No. On the Banach lattice category, these are completely different. Injective objects are completely different because, as I've mentioned, one can prove that there are no injective objects if you just consider lattice homomorphisms. This is I think this is mentioned in a paper by the Pachter and Wickstead. It's and as you mentioned, there are several examples of injective Banach lattices when you take just positive maps.
So I mentioned, I showed the Arendt's paper in my presentation. So maybe it was to see what Arendt proved.
Maybe I should look into that.
Remember exactly.
Thank you. Okay.
This is first my remark. The second, what about the separably injective Banach lattices? Busquets proved that separably injective Banach lattice is the same as injective Banach lattice. Okay, and third, my remark is the following about the circle of problem you mentioned. Probably Boolean-valued approach will be useful, but to say it definitely, I have to know exactly what problems. If possible, please send me some.
Yes, I can send you
papers. Okay,
paper, yes, of course.
And then I will speak definitely. Is it true or not?
Okay, thank you.
So I have a question or remark, because when we started working on conditional expectation in these spaces, we had to extend some results from the classical case, because the classical case, the range of the conditional expectation is R, and now it's we are taking like dedicating complete these spaces with the unit, but in actually we are all time going for wider spaces like universally complete these spaces with unit. So if we take this, can we use this machinery of Boolean-valued analysis to extend the results from the classical probability cases to this framework made by Bruce Watson here and Ferdinand Labuschagne and Professor Wenqi Qiu?
My opinion is that the Boolean-valued approach can be applied in any situation where you have complete Boolean algebra. If your problem or your situation, your structure, you are considered contains complete Boolean algebra, then the Boolean-valued model can be applied and useful. But will be this application effective, interesting? That's the question. Okay, not any application is interesting. For example, you can produce a lot of results interpreting in Boolean-valued analysis different mathematical theorems, but not all they are interesting and useful. Okay, so it depends on the question, it depends on the concrete situation.
Okay, thank you. Someone have a question, please?
Sorry, and the problem that consider Labuschagne, for example, someone else, maybe Grobler,
Bruce Watson and Wenqi Qiu.
Yeah, I think that Boolean-valued approach may be useful for these problems.
Thank you.